Welcome to today's webinar. The topic today is analysis of pedestrian-induced vibrations using linear time history analysis in RFEM 6. We analyze the model that you can see in the preview, the steel bridge. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the content of the website, German and English webinars, newsletters, and so on. I will be the moderator today, and I will answer your questions during the webinar. My colleague Thomas Eichner will be the presenter today. He's the main responsible person for the dynamic add-ons in RFEM 6. I show you how you can ask questions, at least for the attendees who participate the first time. At first, I switch off my camera that you can see the full screen. Just press that button with the question mark, then enter your question here, press send, and I will receive your question. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. Okay, that's at the moment all from my side. I hand over to Thomas. Thomas, it's your turn.
Thank you, Andreas, for the nice word. And also a hearty welcome from my side. We will just start with the content of today's webinar. So in the first step, I will give you an overview on the add-ons, on the dynamic add-ons within RFEM 6 and RSTAB 9 and all their capabilities. In the next step, we will look at our model we will investigate today. So we will also describe the loading, the system itself, as well as the planned investigation on our walking induced vibrations. In the third step, that's gonna start with the program. We will examine the vibrations with the modal analysis. So look on all of those eigenfrequencies of the system. Then we will start with the time history analysis, well, at least with the load approach for it. We will start with the load approach for walking, the theory, and how we can input this in the program. And followed by that, we will continue with the time history analysis settings, some tips for time stepping, and also the results interpretation. Depending on the left time, we will also have an outlook on further processing the results with the help of a fast Fourier transformation into the spectral domain. So let's get right into the first step, which is also like my daily work at Dlubal Software. So here are all the add-ons for the dynamic analysis. You can also click on the link to have a more detailed description. The modal analysis, we will also perform one today. It is almost needed whenever you treat civil dynamics. And so it should be known by most of you. In combination with the response spectrum analysis and the modal analysis, we always have some webinars, some seismic design webinars, which I can just recommend. The response spectrum analysis itself combines the response spectrum with the eigenfrequencies and creates a state of the system, let's say. It could be created by applying equivalent loads, as well as the equation can be solved directly to get directly to the internal forces as well as the deformations. And that's done currently within RFEM. So you can just select on response spectrum and some important modes for it, or let's say 90% of the model mass you would have to select. And with that, the rest should be automatically. That means you get results, you get an envelope of results for the modal combination and the directional combination. And the final result is already automatically inserted in the seismic design situation. And that means it's just considered in the design. So I did that quite a lot, as you can imagine, and I could even do it like in 15 clicks on a model that has its, let's say, normal design completed already. So I would need about 15 to 20 clicks maximum to achieve a response spectrum analysis. So the next thing would be the nonlinear static analysis, so-called pushover analysis. That means the structure is just pushed from one side and the load is increased incrementally. With that, we can also consider nonlinearities. Therefore, it's called a nonlinear static method. And in the end, we get a force deformation curve, the capacity curve of the structure, which itself is a great tool for engineers, since you can just simplify your complex structure to just one graph. So you can compare it just like with a single degree of freedom system by yourself. And the comparison with single degree of freedom systems is also used in this pushover analysis. Currently, we have implemented the N2 method for the calculation of the performance point. That means the performance point is the point where the structure, the maximum deformation point the structure is estimated to have under the defined response spectrum, so under the defined the seismic loading. Then in the last slide here, we have also the time history analysis. And this is going to be the topic of today, so I won't go into detail right now. There's a differentiation between the linear time history and the nonlinear time history. We will look into the linear time history since it's just a simple vibration analysis and we don't include, or we don't have to take nonlinearities into account. Also, the nonlinear time history analysis is not yet implemented in RFEM 6, but I can tell you there are good advancements in the development currently. However, I can't really say a date currently. Okay, let's go on then directly with the program and our system. What we have here is just a foot walking bridge made out of steel and reinforced concrete. The bridge is 20 meters long and 2.5 meters in width. So also we have, our main beams consist of HEB 300 on the top as well as on the bottom. We have some secondary structure here with, or not secondary structure, secondary elements here with just HEB 100 as well as some around 50 H profiles connecting those HEB 300. Also in the middle you can find a reinforced concrete surface array flat. It's just 10 centimeters C3037 and it's just there to treat our floor in this case. For the loadings, it's really important for dynamics in general to try to estimate the real values that occur on the place, because from this loading and the masses we will define, well, if we get the mass wrong, you can't really use the results, right? So let's take, for example, for this model, we will take the self weight and some dead load that accounts for just permanent loads that are built on this structure. Now we could also think about, for example, giving it a snow load on top, right? But it would change the behavior of the structure, the dynamic behavior, since the masses are like different in that case. But more than like 3/4 of the year there wouldn't be snow, so it's not really a good approach in this case. So we're going with these masses here. Okay, so in the first step, we will try to calculate the eigenfrequencies of the structure, which means we will have to go into our base settings of the program. With the base settings, we can go into the add-ons, and all about those dynamic analysis add-ons are within here. You can see the modal analysis, response spectrum analysis, time history, and so on. And in addition, we have also a special solution add-on that's at least a honorable mention. It's the building model. The building model can simplify you like an 8-story reinforced concrete building by using rigid diaphragms into an 8 degree of mass system. So it can help you simplify a system to be able to interpret the results more easy. So we will start with the modal analysis right here. I'm gonna activate it, and we're just gonna go through it quite fast. We're just gonna create this new load case here from type modal analysis. We will create a modal analysis settings, and now we will go for 20 eigenmodes. We will go for full consistent mass matrix, no neglection, only loads in Z direction. So quite standard settings here. There are more explanations on that in our seismic webinar, so feel free to watch that as well. Okay, with that done, we also picked for our masses our only existing other load case. So that's quite easy in this case. And we can just go into the calculation. So that should be quite fast. I think about 5 seconds. That's it. Okay, and then we can investigate on our eigenfrequencies right now. So the first one, well, let's first think about what we're gonna investigate here. So what we're gonna investigate, we wanna have the walking induced vibrations. That means we will apply a foot walker in the middle here, and he's gonna walk over time over the whole bridge. That means we have a vertical loading here, like 2 times, 1 time for the right foot, 1 times for the left foot, and so on. That also means that, for example, this eigenform does not move in any way in the direction of our loading. So it won't have really an impact on our solution here. That means that eigenform is just not important for us. Let's look into our second one, and that's where, well, it changes. Now we have vertical deformation of the structure, and it's in the same direction as our loading. That means this will be a quite dominant eigenfrequency for our results later on. And let's also see, this is now our smallest relevant frequency with 4.75 Hertz. Well, the limit value is 5 Hertz, where you don't need an acceleration check. In this case, we are below this 5 Hertz. That means we need this acceleration check. And that's why we need to perform this time history analysis in the following. So let's also look into some tips how to find like relevant frequencies. Maybe you know it from the seismic webinar already. We have also those effective masses here available. And we see now our second one has like 55% about the y-axis, which is quite right. And with that, we know this loading is of importance. So around the y-axis is important for us. So like everything that has something in here in this column, the next thing, of course, would be the Z direction, which is this column. And there we see, for example, the 8 mode has also like a deformation in the direction of our loading. And here, just another tip, it's not that simple as in the earthquake analysis, where you have like the masses all existing and the masses creating the load. Here you have another load, and only eigenforms that depict in that direction of the load are of importance. Let's also assume, for an example, in this case, we have a walker that walks over that bridge, but we try to perform the analysis by simplifying it and putting him just on the middle load. Well, then the results could also be not so trustworthy, in my opinion, since let's look at the second eigenform. We have no impact of this eigenform for a loading in the middle, and also with the biggest eigenform of the z direction, we also have no impact on it on this middle form. So that's something, well, you could almost also put the loading on the support, right? Not exactly, but like for simplification. So here I would recommend really to investigate your own loading and your first frequencies. Okay, then we can go into our frequency investigation further. We will need our dominant frequencies. That means we have this one with 4.751 Hertz and this one with 11.271 Hertz. And those two values I will keep in my head, since I will use them later on for the definition of damping. Okay? Okay, let's go on with the theory. Now we will try to apply our footwalker forces on the structure. And we have it right here. That's the vertical loading of the walking. It's referenced to a German literature, Bachmann, 1988. It's the original text. There are also newer texts from 2004, but he references a lot to this 1988 version. However, there are a dozen of different possibilities, or let's say literatures, to define the time function for a footstep. So this is just an example, but you could use whatever function you like for the definition. But we will go with this one. So let's go into this function for a second. We will only think about the descriptions below first. What we have here is he gives us a step length of 0.6 to 1.0 meters. And for the first part of this walking, we will only look at the local placement of those loads and not about this time. So we don't care yet about the time, and we will only look at this value, and we will pick a step length of 0.625 meters. So we will have the right foot is there, then we have after 0.625 meters the left foot again after 0.6 meters the right foot. That means we have between one right foot and the other right foot there's like 1.25 meters. And this is something we want to try to apply in the program right now. So we will go in again. We don't need the time history analysis add-on activated yet, because this can be done even with the basic RFEM. This is just a load wizard, and we can find it within our load wizards in the data navigator, and there we have this moving loads option. With that moving loads option, we can just define how our load will be placed. For that, we need first some reference lines. And those reference lines can be picked right here in this line set. I did pick them already, but we can also look at them. And they are just the lines of the left side of our structure in this case. So we will set the parameters of our walker location with reference to this line. Quite simple. So that's also called the trajectory definition. And we can also see it on this image on the right side below, trajectory line. So for the next step, we will have our moving, our step size. Now this is 1.25 meters. Why? Because we have 2 foot, as I just explained. Between the right foot and the right foot, there's 1.25 meter. And with the next thing, we will go with an eccentricity. That means we want to have the distance between the trajectory and the place of the loading. For us, we know the bridge is 2.5 meters in the width. And with that, we can say we will just use 30 centimeters horizontally between left foot and right foot. That means we need here 1.1 meters. And we will have an offset of 0.625 meters. That's just because I don't want the load starting at like the first, like right at here or here, because that's just not needed. Like I assume that's just not dominant for us. Okay, or just not having a big impact on the results in this case, since the supports are just next to it, right? Okay, but with that we have the geometrical stuff given. The only thing more is we need to also select the surface to apply those loads on. Lines will be possible also soon, just as a hint. So it's not only restricted for surfaces. And with that we have everything done here. Now we have to define our load. And this can be done here by picking, okay, we have one lane with a load factor of 1, that's okay. Now we can create our new load model. This will be just a single foot walker in our case. And we will just go for a unit value of 1 kilonewton. This 1 kilonewton, in general, we would want to use 0.8 kilonewton of the loading of the foot walker. But we have multiple ways to achieve it. Like we could place it here 0.8, or we could place it in a time diagram, or there are some factors in a program, and you can just decide on your own where you want to have the right value, and on all the other values you would need to use unit values. So we will use the unit value here, and I will show you the 0.8 later on in the time diagram. Just for your information, there's also several loads. We could also go for axle loads for vehicles, and yeah, so a lot of more features within this load wizard available. Okay, so we have the first one, and this will be our right foot, and we will directly just copy it. Well, we can also look in the right foot again and in our load cases. There we will see we now have 16 load cases created for us. And we will also set them, just because we're in dynamics, I'm going to go for seismic actions. Okay, we will look at the loads graphically as soon as we have the left foot as well. So let's go and call this left foot in this case. And well, the loading model stays the same, so we only have to adjust here the moving step is okay, and we have to adjust here the eccentricity, so we need to do plus this 30 centimeters. And now I'm just thinking about I think I did something off here with this value. No, that's quite okay. Okay, 1.1 meters, then 30 centimeters. Okay, so we will need 1.4. Okay, that's okay. 1.4 meters right here for this eccentricity. That means we have 30 centimeters in between the 2 foots. And for this, we will have 1.25 meters of offset. That means this one, this left foot, would be the one that is on this edge, but we don't take that, so the next one is one distance apart. Okay, now we see here that we only have 15 node cases in comparison to a right foot with 16 node cases. Well, that's just dependent on the geometric, since the left foot needs just one step less. Okay, with the done, we can also go here and let's go from this side like this. We can go and start our animation for our loading. Can also, we could also change the speed here, make it slower and everything. But yeah, that's our loading. We also see our trajectory, well, our lane lines here. So we will have this foot walker in the middle, and he will just walk straight up this bridge. Okay. So now we have the locations of the loading, and now we need to take care of the time of the loading. When will it appear, and how long will it appear? For that, we will go into our equation again. And for those who already know it, this here is a Fourier series with 3 harmonics. We have here our step frequency, Fs. We will pick it as 2 Hertz. This rest here is just a transformation into angular frequency and a Fourier coefficient, or it's like the weighting coefficient. And we also have a phase shift. So, and therefore I prepared some simple Excel for some understanding here. What I did here is I just plotted those 3 parts of this Fourier series. This means we have the first harmonic. This will have an amplification factor of 0.4. We have the second harmonic with 4 Hertz. So the first frequency here is 1 Hertz, the second frequency 4, and the third frequency 6. They are called first harmonic, second harmonic, and third harmonic. And we have also a shift of pi½ for the second and third harmonic. We can see from the step frequency itself that our period is 0.5 seconds. So we will also have a 0.5 seconds length for each loading. With that, there's one more thing. I will not, I just didn't implement it in my function. But what you can see here is that the phase shift of the second and third harmonic makes it to a minus cosine function, basically. That means the minimum of this whole function will not be at the 0 point, but a bit to the left side, depending on these Fourier coefficients. In our case, it would be 0.03 seconds shifted. And that's something we would need to implement in our function here as well, if we want to consider it. But I made the assumption that it won't change the results with a big impact. In the end, we go for 0.5 seconds, and we have the same amount of loading, just with a bit of a different factorization, right? So there shouldn't be a big difference or a difference at all, in my opinion. So that for this understanding. Now we can go back here. We can also see big peak and small peak. And we can just, well, let's just define it in our software and inspect it there further. So at first, we will activate our response spectrum analysis. And with that, I meant, of course, the time history analysis. So we will activate our time history analysis. And, well, as a hint for it, you can find also our dynamic loads on the left side on the data navigator. And we could just change time diagrams really fast by just accessing them with the data navigator. It's, in my opinion, the fastest way currently. However, we will go with the ones in our settings, in our load cases and settings. And yes, so we will start here. First, just some general information. We can create time history analysis in load cases. That said, we can create, let's say, the time diagram one, where we would select a time diagram, and all the loading that is defined within this one single load case will be modified with that time diagram. However, we have like, I think, 31 loads on load cases, and that means we will have to go with the load combination variant, where we can assign multiple load cases and time diagrams. Okay, so for the next thing here, what we also can do is we can select the time history analysis of accelerograms. The good thing, we don't have to take care of the placement of the loading, because it's just prescribed by ground motion and supports in this case. And with that, we have just a possibility to create accelegrams either with the table, or we can also, of course, take our really quite big accelerogram library here. Just quite easy. Just pick the one you would estimate, and then you could investigate on the behavior of the structure under this accelerogram. Okay, but that's not the thing we need today. So I will delete this one load case again, and we will go into our load cases. In our load cases, we will create a new one that is called time history analysis. This one, we will ignore this first page for a few minutes and go directly into our assignment sheet. So we don't have something to do with the time history theory yet. We still are just in our loading. So we did our placement of our loadings, but now we will also have to apply the time. So we will have to apply this function according to Bachmann. And with that said, what we want to do is we want to apply all of our load cases right here. Now we see we have all the 16 right steps and all the 15 left steps here, and we can assign them like a time diagram right here. With that, we will go for a new time diagram, and I will just copy paste my function in here, since that's a lot of typing in this case. And there it is. And this here must be away, and this here must be small. This here can be n. Okay, so, and there it is. What we have here now, we also multiplied it with the number of our footwalkers. We multiplied it with our factor g, and we took the function with the Fourier series in it according to Bachmann. What we now see here is we have a factor of 2000, so there seems something wrong. And that's within the used global parameters here. So I used n, I used g, and I used fs. And now let's look at them. Since I predefined g with 0.8 kilonewton, but this is just a function, so it's dimensionless, the program will automatically calculate functions within SE units, which means this is like an 800 in this function here. It means we will have to divide it by 1000. Then we also selected the number of footwalkers, which is 4, and the step frequency of 2. That means if we want to change the step frequency in the end and just press calculate again and have the results for it, that is possible with this global parameters quite easily. Okay, So let's go first for this G adjustment, and then I will explain you something about our number of walkers. This divided by 1000. T max is 0.5 since our length, our period was 0.5 seconds. There it is, big peak, small peak. And we have a maximum factor of 2.5. Mainly because of this dependence on the number of walkers. And so it would be between 0.8 and 1.6, I think. Okay, but with that the function is defined. Now let's look into our walking theory again. Just as a hint, there's multiple functions for that available. Also for horizontal loading, where just like the influence is quite lower. And also the frequencies are kind of split by half for it. And there are also functions for jumping or running. For jumping and running, there's one more benefit, and that's that there are time intervals where no loading is on the structure, because no foot like touches the structure. Okay, let's go for the amount of persons. Well, in general, we have to design for the reality, and it's common that not only one person walks about the bridge, so obviously we have to take this also into account. Multiple persons normally don't walk synchronously. They just walk on their own, and that's quite random, except for like military structures where you have like an army marching over the bridge. Then there could be also this synchronous increasing necessary. For this today, we will consider the change in location. Like we have a change in the loading location. And therefore, if our fundamental frequency would be below 2.4 Hertz, we could go for n is 4. We will also go with this approach, simplified. Generally, the number of persons is limited to 9 persons. And the main thing I read about is that this value is estimated by what's estimated to happen, right? So if you estimate to have a bridge in a rural area, you can go with a lot of, with quite less persons than if you compare a bridge in New York or something. So that's something you just have to take into account here. And there's also a simplification if you neglect the change in location. So if you have just one load on a location, but that's quite hard, I would say. For our structure, it's 50 square meters, and it says 0.5 persons per square meter. This would result in 25 persons. So if we would insert 25 into our formula, we would have quite a high loading factor here. And that's not quite good. But what I would do in our case, I saw that the second eigenform is also like a second eigenform. That means it has two waves in this case, or two bowls. And that's why I also inserted this factor 0.5, because I think it's okay to just consider half of the bridge with that dominant eigenfrequency. Okay, then we can go into the program again. Let's go here. And well, yes, that's where the n comes from, right here. So quite good. Now we have selected one time diagram only. We will select it for all of our time functions. And now that's the great benefit in comparison to RFEM 5. One more thing here is we need to also apply our time stepping or time slip. And this exactly time slip is new within RFEM 6, that we can define it directly in this table. Now I will just go. The first right foot is at 0 seconds. Then we have the second right foot 1 second. Well, there's always 1 second beneath, right? Yeah. So we will just go here and fill it up to 15. Then our first left foot starts, and this left foot, the first left foot starts at 0.5 seconds. Then we just need to increase that always by, well, 1 second again. You could also, of course, use, for example, a table program like Excel right here to just fill them up and copy paste them right here. You could also use the syntax input here on the bottom side, where you could also just, it's quite understandable how it's built up here. And there you could go with a coding help to create an automatism for it. But I thought I'm just gonna insert them right here because that's like 1 minute. That's not that hard. So we have that here, and now I'm gonna show you what the difference is to RFEM 5. I did this calculation also analogously to RFEM 5 within here. And with that, we see in RFEM 5, it was needed to create one time diagram for each loading. That means we also had to create 33 time diagrams in that case. And we had to adjust every time diagram, this value and this value. So that took like 15 to 20 minutes. And if you did it the first time, even longer. And if you did a mistake, oh, that's not good because it's difficult to find. So with that said, this is really a great benefit within our RFEM 6 right now with this time slipped option right here. Because as you can see, we're done already. We're done already with the assignments. Now we only have to take care on our analysis itself. I'm just gonna go here and go for the linear analysis. So now we can go on. We have two time history analysis settings, right? One is the linear model one, and the second one would be the linear implicit one. The modal one uses a modal analysis, which we pick right here. And it also takes all this information, consider initial states, structure modification, and the masses. It just extracts them from the modal analysis. So the setting making is really simpler, but on the other hand, you had to create a modal analysis beforehand. So you did that kind of before already. Now we can go in and look at the next benefit of this solver type, and that is we can either use Rayleigh damping, but that's not the benefit. The benefit is we can also use a constant loss damping value here. And we will use it, and I'm quite happy whenever I can use it. Because 1% damping value, we will use 1% damping for our structure here. From literature, I saw that is quite high. So I would recommend to look in the literature on your own projects for it, because this, I think it's about a factor 2, at least too high. But okay, let's go here now. We did the damping. Now we can take care of our time stepping. But before we take care of our time stepping, I will also introduce you the linear implicit Newmark variant. With that, we have to make the settings for masses again, since we don't use a modal analysis in this case. And the sad thing, or the thing that sometimes occurs in some problems, is we have to use our Rayleigh damping, so our stiffness and mass dependent damping. We can use two frequencies to calculate those dampings. So we will go also here with 0.01 and here with 0.01. And then we will select our frequencies. And that's why I said I did, just think about taking them right in the modal analysis. And our first dominant vote was the 4.751 Hertz, and our other one was 11.271 Hertz. There it is. So now let's talk about this damping approach for a minute, since I see a lot of confusion on it. This damping approach is something called mass and stiffness dependent damping. Mass dependent means the alpha value just kind of is a factor for the mass matrix. And the beta value is just a factor for the stiffness matrix. And in this way, the damping matrix can be described as a multiplication of those damping matrices. And with that said, for the alpha vector, what it does is it shapes a frequency that starts at infinity. So the asymptote here would be this y-axis, and the asymptote on x-axis is the x-axis. The beta value, what it does is also adds an additional asymptote beginning from the 0 point, from the origin, and with a slope that is defined right here. So as soon as you enter beta damping, and you would have like an infinity frequency, this infinity frequency would have an infinite damping kind of. And that can lead to problems, at least in non-linear time history. What you want to do in general is the frequencies you estimate to have impact on your results should be in between this frequency range. If it's like 10% off or something, that shouldn't be big of a problem. But if you're kind of double of the second frequency, then the damping approach is just not right anymore. And one hint for at least non-linear time history convergence, if you had contact with that analysis already and you didn't get your analysis to converge, just try setting this beta value to 0. Because with that, I don't know what is in the model, right? So if there's a really, really stiff object in the model that could be like on some value of 30 in this diagram, then that would result in extreme convergence problems. So, and with setting this to 0, you wouldn't have the problem to have an infinite damping for whatever frequency. I mean, except if you're in the first range, but that's another topic. Okay, for today, we are in the linear time history, so that was just an excursus tip, kind of. Okay, with that done, we can go out of here as well. And we have now our two analysis settings. What we didn't do yet is we didn't think about our time settings here. And well, this is quite important, one of the most important things within the time history analysis, the time steps choice. And it's a trade-off between the accuracy of the results as well as the calculation time. I mean, you have to think about each time step is comparable to a normal static analysis. Well, a little bit more complex since the dynamic equation is just a bit more complex. And for each time step, you have one of those analyses after each other, because you can't do it in like parallel, but you have to do them after each other. And that's something where the calculation time, unfortunately, can explode. Okay, so here there's just some recommendations. So if you have a function-based excitation and in general have some knowledge on your frequency structures, I mean, mainly you always do a modal analysis beforehand. That means you would pick the highest natural frequency, and the time step is just the highest natural period divided by 20. That's the same as this formula. 1 divided by f is t, so t 20. And the same as well for the excitation frequency Fe. Also here, Te divided by 20. Just easy. If you take something else, so if you take like a transient defined excitation with our tables definition, then you would aim for 7 time steps in between, like the shortest change within the table. I mean, if you have a table which just has constant values, you don't have to take 7 time steps in between whatever you defined there. But you need to investigate, okay, where did a change happen to where did a next change happen? And this region you would have to split into 7 time steps. For today, I will go into something what did excite me for a bit. And that's the so-called fast Fourier transformation. So what we want to do here is we will take the results out of RFEM in the end, and we will look at the results not in the time domain, but in the frequency domain. And this fast Fourier transformation has some things you have to consider or take into account beforehand, so it will be easier when we really do it. And with that said, here's just for an example the finished fast Fourier transformation with our model results in the frequency format. And here, this Excel sheet will also be sent to you. With this on the right side, the left side, we don't care about the left side. That's something we will achieve later on. We will care about the right side. And what I defined here is just my min and max frequencies. And then there's this rule that we need to input values which have the amount of 2 with n above. That means, like, we need, for example, if we have n is 10, we need 1024 input values. And with the frequency, we can also calculate our time step size in this case. You can find the formulas in the Excel sheet itself then. And with that, I defined just we will take a 0.015 second time step. Oh, I'm sorry, I will go a bit closer here. So we will go with this 0.015 seconds time step, and we don't care about like initial swings or the first few seconds, since they could they always have some strange results, I would say. But we will just ignore this, and we will take this into account anyway. So what we do here is, without the transient time, we have a maximum time of 15.345 seconds. This will lead us to a frequency range of 0 to 66 Hertz. And if you know something about this depiction, then that means we can investigate 0 Hertz to 33 Hertz with this analysis, with these settings. Which means that helps us kind of. We know with that 33 Hertz is our maximum frequency that is investigated. That means if we have some natural frequency of 50 Hertz, then we made some wrong assumptions here. Then we would need to readjust our time stepping. But okay, let's go with that into the program and just set this time step. So this is 15.345 and this is 0.015. And I've just thought I'll do so this is the saved time step with 0.0515 seconds. This is what produces our data. And this is our accuracy time step. That's used for the calculation. So all of these time steps with this combination, we have a calculated time step of 0.005 seconds, but only every third time step is saved. That's something just since every time step has quite a lot of results. We need this, well, it is needed to reduce the data size. Like 20 gigabyte models can happen in this analysis quite easily. So that's really a point here. Okay, we will do the same with this second one. 15.345, 0.015, and 3. And just as a hint, if we just copy this analysis and would change it here to linear model, it would be faster. Just an efficiency tip. Okay, with that done, we are here okay. And we can click on calculate. And while it's calculating, I can go on the difference of those two analyses again. Let's cancel it again. I did forget somehow one of those. Yeah, I just didn't do it. Okay, let's call this first load combination linear modal analysis. And then I did forget to apply a second load combination and apply the Newmark analysis settings for it. Exactly. So here, as we see, we have to define the masses, a mass case in this case, and not a modal case. And we have access to our structure modifications as well as our initial states, final state type, and stiffness type. So also that's a benefit here, because in the linear model or in the modal analysis, we can't use the final state, initial state, final state one. Okay, with that done, now we can go into calculation. And what we see now, well, the first one is already started to calculate this linear model settings. And we see how much faster it is, right? So that's the benefit here. And the problem with this first one is we only have global damping. So either Rayleigh or the Slers damping. That's a problem as well as a benefit, right? So we have a simplified possibility for considering global damping, but on the same time, we can't use local dampers. Local dampers are only available within the direct time integration. So there are damping problems and benefits in both variants. Okay, let's see. I know it's gonna calculate like 115 or something, but I just wanna go on. So I prepared the results as well. One thing I forgot in the calculation process, the time history analysis, you can do multiple like parallel, right? So as you just saw, the linear model one was calculated at the same time as the NUMAC one. So since those calculations do take quite a lot of time and they are not that good, one single time history is not good to split into different calculation processes. That means you would need one core. I mean, you can enhance some of it, a bit of it, but in general, you have one calculation that's after each other. So if you just do multiple time history analysis, the time won't increase too hard, but in the end, you have different results on different investigations on the structure. I mean, you could use structure modifications where you increase the stiffness, for example, of just four of those, of all of those HEB, and so on. So you could just try to think about what are you gonna be interested in, what influence of some changes in the model are you interested in, and define then before the first calculation kind of, and just go for 4 time history analysis with different structure modifications at the same time without losing too much calculation time. That's another tip there. And now we are almost at the end, I guess. So let's go into the time history directly. What we see here is, on the one hand, we see our loading also. That's quite nice. See our loading steps are also here. And within the time history analysis, we have access to like every result on the members or on the surfaces. So that's right here, as well as all the graphical results. But as soon as you are interested in time-dependent or results over time, you would go into our calculation diagrams. And with that said, I already prepared some just for your information. As the node 94, I picked this one here. So it's in the middle of the left side of this bridge. And that's the point we will observe right now. Let's go for the deformation. So with this time diagram, we're going to select the time history analysis. Time is preset. We will have to select what we want to investigate, the direction, and of course the node. I did this already for the deformations, the velocities, as well as for the accelerations right here. And now we can look at our amplitudes. For the linear modal solver, in the displacements, we have a maximum amplitude of about 0.1807 compared to our NUMAC one. Well, that's quite higher. That's like 0.5, almost higher. So I would say this is not exact enough, this first linear NUMAC analysis. And also linear modal analysis. Let's go. CO2, that's our linear NUMAC analysis. So that's our more precise analysis. And with that, we also see here this big peak and small peak that we had in our time function. This leads to my assumption that within this graph, there would be our excitation frequencies, 2, 4, and 6 Hertz. Okay, that's just my first assumption. And then we can also go for our accelerations right now. And for that, we need to jump one time to the PowerPoint again. There are some limit values given for the acceleration for this check. Bachmann has one recommendation of 8% G, which means 0.8 meter per second squared. The Eurocode is a bit stricter with 0.7 meter per second squared. But let's just remember 0.7 to 0.8. That's our limit. And yeah, now we are in our CO1, so the linear model, and we see a value of 0.018. Now we could think, perfect. We have our check fulfilled. That's great. But also let's look at our more exact solver in this case. There we see our RMS value, so our acceleration in average is 0.073. So there's a big discrepancy between those two solvers, right? And this is, let's say it is at the limit. I mean, the limit is either 0.007 or 0.008. So we are at the limit. So we should think about like changing the masses of the system or changing the stiffness of the system to influence the eigenfrequencies, or to have dampers placed on the structure. But one thing here, the difference between those modes, between those analysis types. What I also did, this here, this linear time history analysis, uses 20 modes. The one I'm gonna show you right next will be the same analysis, but it's gonna use 50 modes. So 0.018, we switch it, and there it is, 0.066. So that means it was really important to use more modes in this. We are not quite at the direct integration solution with that. So there could be even more modes needed. But that's quite okay, in my opinion. Well, if I think about it, the one check is not fulfilled and this one is fulfilled, so maybe you should think about that as well. And okay. So for the last thing, I know we are a bit over time right now, but I will do it as shortly as possible. What we want to do is now we take our deformation results from here. We can inspect the table. And as we see, we now have exactly 1024 values generated. That's because we did this time settings according to this fast Fourier transformation Excel sheet. And with that, we can go. Yeah, we can just save it. That's okay. And there is our table. Right here. Now, I will try to do this quite fast. The Excel sheet with the fast Fourier transformation you will also get. What I do is I do copy from one existing file every column from E to the end, or not to the end, just what's filled here, like this. Then we will delete, unfortunately, we have to delete all those results, that existing results, as well as this one value. And now, I mean, it's everything explained somehow in German here, but I also added the links here on top where it's just, described in English as well. And also, it's quite important to use this link because you have to, make this data analysis available within your settings. And with this data analysis, we can jump into our Fourier analysis. And we can depict our values here. So for the input, I did take our UZ values. And for the output, I just picked the one on the right side. And also this Excel table, what it also helps, it gives you, as you can see, D3 to D1026. I got those values here as well. Oh, now I changed something. That's not good. Now for D3, what? D3. Okay, then I did. Okay, we need a double point as well. Done. Fourier is done. Now we can take those 3 that I left from the previous slide, just move it to the bottom. And then we can go back up again in those 2 columns. Input diagram, just one diagram you like. And there it is. We have our results in the frequency domain. So, I mean, it's really done fast, in my opinion. I mean, this was 2 minutes, I guess, and we are in the frequency domain. So what we can see here now, we have the first point. I have quite some understanding issues there. So I can't really explain this first point in this case. But what I can explain is, for example, the second point, which is just the first harmonic, the second harmonic, and the third harmonic. So that fits the assumption that we had when we inspected our small peak, big peak deformation time diagram. Okay, I did the same also for the acceleration as well as for the velocities. But to be honest, I'm not that. I can't explain them correctly. So I think some of you could explain it way better than me. Okay, so here we have, that's it. So with that, we can go back into our PowerPoint for a second. We have our acceleration limits. Now I also did show you the transformation between the time domain and the frequency domain. And in the end, I also want to give you the list of the literature used for this webinar. And it will also be sent to you afterwards. So all this, you will also be able to download the model as well as the slides and everything. So we are finally through. It was a pleasure to talk about this stuff because it's really making joy to work on those time history analysis, especially on footbridges. It was kind of fun to prepare this webinar. I hope you had kind of a similar fun with it, and I wish you a great rest of the day. So I think, Andreas, you wanted to also say something in the end? Oh.
Thank you, Thomas, for your nice presentation. I have an additional hint for you. You can book our online courses. For example, the RFEM 6 course. This is for beginners. And you can also book the Eurocode 2 or Eurocode 3 course. For more information, you can click at the buttons above, at the bottom, or you can scan the QR codes. Then you will find more information and the prices and so on. The courses consist of several chapters. You can interrupt the course anytime and continue when you have time again. Okay, that's also all from my side. I thank you for your attention. Thanks to Thomas for this presentation. I wish all a nice rest of the day. Bye-bye.